All right, good morning, everyone. Today we're going to go over a real important topic that is going to kind of carry through the whole year, and what we're going to do is talk about electrons. So I'm going to say a disclaimer once, because I don't want to keep saying it all hour. Last year when I did this, I did it over and over and over again, and I didn't need to. You're not going to understand this in the beginning. It's going to be confusing. There's different ways of teaching this. But how I'm going to try to teach this is I'm going to teach you about the ins and outs of it to the level that we need while showing examples. So please don't have a fixed mindset or a closed mindset where after I show one example, you're like, I don't get it. Oh my gosh. And then all of a sudden grumbling start to happen and all the murmurs, and it's harder for me to teach and move through that. Just understand, and I guess just have faith and trust that by the ending of the worksheet, you're probably going to understand this pretty well. But you won't in the beginning. So just take in everything you can and know that every time that we move forward, a little bit more is going to be revealed, and the comparing and contrasting from one problem to the next, by the time you're done, it'll make a lot more sense. What we need to do today is talk about where electrons are located, where they live. The more we know about where electrons are, we can start saying why this thing explodes, or why this thing doesn't, or why that reacts with this. It's huge. It's such an important thing. We're going to be exploding an element within the next 2 weeks for you, and you need to understand why it does that. Well, it's based on the electrons. Okay? So the sheet's a little compact, a little confusing, but I'll guide you through it when you need it. So what we need to do a little bit is talk about first where electrons are. So I'll kind of let you know where you're writing. So this was Bohr's model, and there's nothing to write yet. Here's the issue. Those location of electrons are way too specific. I mean, it's like a train on a train track where it's just right there, right there. That can't be. How small these are, how fast they're going. There has to be a different kind of an image that probably exists with the electrons. So we enter this thing called the quantum theory. Okay, now you don't have to write any of this yet, but what it does here, we'll write this. So you get quantum theory way on the top. It's the location of electrons. It's based on probability. So it's not like we're being as exact. We actually have to take a step back and go, whoa, maybe we're a little too precise. Okay, maybe we don't quite know everything about it. And they started learning more and more about particles, and why we studied waves a little while ago is that they figured out that particles move and behave like waves. So their patterns and their locations can be determined a lot through properties of waves and energy. So this is called an electron cloud. And a cloud is fuzzy, right? If you said, oh, I'm kind of cloudy on those details, maybe you'd say that, maybe you wouldn't. But if someone said that, you would be like, oh, they know exactly what happened. Oh, did you see the accident? It's a little cloudy. Oh, they don't really know all the details. It's a little fuzzy. Well, it's 90% of the electrons' locations. We'll label that in a second. But it's not like there's 1,000 electrons here. It's all the possibilities of where it could be. So the denser it is, the higher probability. I don't have it up here, but one of my favorite pictures are like those, either the world maps or even just the United States maps at night, and then you see where it's all lit up, you know? It's like Chicago and New York and Los Angeles, and then like Montana is just black. Because the density of where they are is lower, so there aren't going to be as many lights on, so you won't see it as well. Same idea here. There's a lot of electrons here. There's not nearly as much here. There's just a few out here. Well, what is this all about? So there's a thing there. It says Heisenberg uncertainty principle. Just find that, please. I know we're skipping some things. What we're going to do is we're taking a step back, and we're going to utilize the Heisenberg uncertainty principle. What it says is it's impossible to know precisely both the velocity and the position of a particle at the same time. So if you're a Breaking Bad fan, maybe that's what you're thinking of. You've seen that on Netflix. But this is actually the Heisenberg. But that's where he got his name from. If you've never watched the show, the chemistry teacher, main character, has to come up with kind of an alias, and he uses Heisenberg because he's a chemistry teacher. So this is where it comes from. The electron's so little, it's moving so quickly, and we can't see it, is that if they isolate it and try to take this in for as much as it's worth to you. If you try to isolate it and try to find it, then you really don't know how fast it's going. Because you had to, you disrupted it, or you don't have enough information. You've just located where it is, so you don't really know about the speed. If you figure out the speed, the velocity of it, and you're able to determine that, you really never know where it is. It's never in one position because you're trying to determine its speed. And that's kind of the mantra or the overall umbrella of kind of saying, hey, this is more on probability. We don't have such a precision of what Bohr's model looks like. And there's a lot more to this, but for our purposes, this is what we need for now. Okay? So, saying that, I did a little study. So I took a picture of the school, and what I did is I tracked myself every 10 minutes, let's say. All right, so that's me. Hey, I'm by my room. And oh, I'm still by my room. So this is a low energy day. I'm not doing a lot, even though that's probably actually moving quite a bit in my room for every 10 minutes. And you notice, though, it's not like there's 7 of me. There's 1 of me. But I'm tracking myself, just like there were 1,000 electrons, but it makes a pattern after a while. So I just keep going. Oh, maybe I talked to Mr. Anderson. Oh, I went to go get some food. And basically what you notice is a simple pattern is being created. Okay? So that's a low energy day. Well, what we're going to call this is called an s orbital. So in the upper left, you'll see there's a little like electron cloud that's a sphere, okay? Then there's an arrow moving down. The arrow is going to be pointing to 2 different orbitals. They're going to say the same thing. So let's just write down the thing we're going to say for both. Is that these clouds are saying that there's a probability of 90% of electrons in that location. Like whenever I see an electron cloud, that's roughly 90% of my electrons will always be in that area. Again, this is not a picture of every electron. Those are pictures of locations where a electron or maybe 2 electrons were at any point. Just like this is not saying that I have a doppelganger, many twins all running around. I guess they wouldn't be twins at that point. But if I had duplicates of myself, that's not what this is saying. It's where I've been and what's the probability. So if you found me on another low energy day, you could say like, well, we could look there, but my odds are that they're there. He's right there, right? Okay, so another day, I have a lot of energy, or maybe I got to do a lot of stuff. So now I'm all over the place, and I'm creating a much different kind of. Oh, I went out to go with my car. I actually think that was my car. That's why I did it there. And I'm moving, and oh, I went out to the tennis court. So there are a few outliers there, but in general, I'm creating a pattern again. So there's a pattern that becomes more complicated. And what I'm trying to kind of duplicate here is what we call a p orbital. So again, as I just said before, it's the probability of 90% of the electrons. Okay? So when we talk about electron clouds, I like to use balloons a lot. So an s orbital, there's nothing else you need to write for a moment. Don't freak out about this. An s orbital is basically a sphere. So I took this dodgeball, love dodgeball, and it takes a real simple shape, and 90% of the electrons are in that location. If I look at a p orbital, a lot of times people call it like the dumbbell. I know it wouldn't actually look quite like that, but these are the ones I lift. It helps a lot. It has 2 lobes, okay? So you go from like 1 cloud to 2 clouds, but they could be in either one. And what it is, it's based on wavelength and patterns and all that, but what you just need to understand is it's getting more complicated. Well, here's the trick, and this is where take in as much as you can, because you're still going to be able to apply this and figure this out, is I have maybe like a simple shape 1s. Well, this is also a simple shape. It just got bigger, so maybe a little higher energy. You don't have to write any of this. But then, here we go. Why do I have 3? It says 2px, 2py, 2pz. Well, I want to show you. So your job is to start knowing how many different orbitals. You are not having to draw all these. My goodness, you don't. But let's talk about this for a second. So there's an S, and there's only one of them. So you have a little pyramid on the top of your notes, and I think it says blank orbital. Is that right? So write S, please, and then write a 1 maybe with it. So that's my picture of an S. Why is there only 1? Because if I am talking about probability, and take this in as much as you can, and this is the shape. If I was able to actually put a rod right through the middle of it and spin this like perfectly, you would not, it wouldn't, besides the logo, here, it shouldn't take up any, I'm trying to get my finger perfectly, it shouldn't take up any new space, right? It's this perfect sphere. Like it doesn't take up, all of a sudden it's like, oh, magically there's part of the clouds over here. It's a perfect sphere, so there's no other way in space that it's going to take up in any kind of 3-dimensional spacing besides what it already is taking up. So there's only one probable shape. But as we get more complicated, we have p's. So this is called a p orbital. There's 3 of them. Why? Because you could have an x orbital. Think of 3 dimensions. You have an x, you have a y, and you have a z. Okay? That's the 3 dimensions. If I have an x, and then I have a y, and I have a z, aren't those taking up different spaces in 3 dimensions, right? Like there's nothing here right now, but also, oh, now there's something there. There's nothing here. Oh, now there's something there. So you can't just say, oh, this is all it takes up. Yeah, but what if it was orientated this way? What if it was orientated this way? You can't do it for this. Well, what if it was orientated this way or this way? It's like that doesn't take up new space. So I'm going to try something here. It did not work last hour, but let me see if I can get better at it. I'm not making animals on request, so just don't ask. Oh boy. Oh, almost. I gotta move one. Right, we're just gonna leave it. I was trying to match up the colors, but that's just not gonna work right now. So I can have my x, my y, and my z, and it's actually gonna take up, there's 3 different orbitals right now, and it takes up all that different space. I gotta try. I have to try. So it'll take up different spaces. Oh, shoot. I got greedy. And that's why we need to know there's 3 of them. Now, notice, again, it went from 1 cloud to 2 clouds. Check this out. Now there's 4 clouds. It is not your job. You're like, well, that's not 4. This is really weird. It's a cloud on itself. It looks like a belt. But as we get more energetic and more lobes, there's more possibilities. That's all you have to know. It gets more. And what's nice is there is a trend to this. So this is called the D. Please fill that in. You have the shapes. You do not need to memorize anything past the S and the P for what they look like. So a D orbital has 5. And it's 5 different configurations in 3-dimensional spacing. The last one, check it out. I went from 1 to 2 lobes to 4 lobes, or we could call them clouds, to 8. 1, 2, 3, 4, 5, 6, 7, and there's one back there that's 8. And this is called an F, and there's 7 of them. So, and we can count by 2s and odd numbers, 1, 3, 5, and 7. Right? And we're going to be using these letters a lot. So these letters aren't something we're like, I don't need to worry about these letters. S, P, D, and F are going to be really important, but we're going to practice them a lot. So, regardless if you're quite understanding that or not, what we're going to be doing is we're going to be placing electrons where they live, and where they live are in these energetic electron clouds. And the more complicated they get, that means the electron needs to have more energy to be in them, just like my picture when I did a simple shape versus a more complicated shape. So please don't copy this down right now. This is called the Aufbau principle. Okay, so you have that right there. I think that's the last thing we have to fill in. It's called Aufbau. It's German. It says each electron occupies the lowest energy orbital available. Please write that in. So what we're going to do is we're going to have to fill the electrons. They always fill the lowest energy level first. As teenagers, it's not your fault. You're going through a lot of surges of chemicals and expenditure of energy and growth. You get tired really fast. So, and some people would deem you lazy, but sometimes you're just tired. Maybe sometimes you are lazy. But it all goes hand in hand, but you would do the lowest level energy thing first probably, and then you go up. If you have to do something else, it's going to require a little bit more energy, and so on and so forth. Well, notice, this shows, don't copy it, the energy levels based on how much energy it takes to be in there. So check this out. Energy level 1 has just 1. Energy level 2, wait, it has 2 sublevels. Wait a minute, 3 has 3, 4 has 4. Each energy level gains what we call a sublevel. And the order gets weird. It starts to get funky. Like all of a sudden, wait, why would that be before that one? We'll talk about it later. But you don't have to memorize that. We're going to cheat instead. It's called a cheat pyramid. This is going to be your lifeline. So there's a box that says cheat pyramid. Please copy this down, not the colored area, and start in the upper left, write 1S, and do it the way that I have it written. Line it up exactly. This will be the biggest, most important thing that you could have when you're doing all of these problems, because it applies to every problem you're going to work on. So you do 1s through 7s, and then notice the second level gains a sublevel. So do 2p to 7p, 3d to 6d, 4f to 5f. Write it nicely. Get it organized. This is going to help you figure out the order. Now, eventually you won't have to have this memorized, because you're going to learn that this is hidden on the periodic table. Not this exact thing, but it is hidden there. When you're done with that, we need to know the order. So what you do nicely and neatly, you are going to place the arrows the way that I have them. So make sure they are going downward from upper right to lower left, and they are crossing the same ones I'm crossing. Once you get a rhythm, you should be able to do it quite easily. And then make sure you have an arrow in the lower, on the left side of that line when you make it. So this tells me my order. What goes first, what goes second.